Well,
Hope everyone's doing well. It's a rainy day in Philadelphia today. All right. So I want to talk today again about revenue maximization. We're going to continue thinking about revenue for the next several lectures, but I want to talk today about a format that is different than an auction. Okay, this is actually something that's much more common than to run an auction, which is just to have prices. So to recap just a little bit, we've studied auctions now for the last 4 lectures, and we've seen how to do a bunch of things with them. So we've seen in very general settings how to use an auction to maximize social welfare with the VCG mechanism. And we saw, at least if we were in a simple single parameter domain, that we could maximize revenue in expectation given a known prior distribution on agent valuations using what turned out to be a pretty simple auction as well that looked kind of like an eBay style auction, a regular old Vickrey second price auction, except with a reserve price. But auctions are difficult to run for a number of reasons, and there's a reason why we don't see that many auctions in real life, not least of which is because you need everyone there at once if you're going to run an auction, right? Like if you're going to try to run the VCG mechanism, or if you're going to try to run the revenue optimal auction that we derived last time, you need all of the bidders in the room at the same time. They all need to, in a coordinated manner, submit their bids, and then we need to clear the auction somehow, compute the allocation rule. And that works sometimes. Sometimes we run auctions. We auction off things like art and real estate, sort of expensive things, when it's like important to make a lot of money. We run auctions on eBay, but most things we don't auction off. Instead, the way we sell most things is we set prices, and people arrive in some asynchronous manner, right? And a price is just a take it or leave it offer. When someone shows up and they see that, I have a used car for sale for $10,000, if someone shows up and is willing to pay that, then I'll give them the car, even though I don't know for sure that there won't be someone who'll show up tomorrow willing to pay $15,000 for a car, right? I could have discovered that if I could really have run an auction, but there's no way for me to gather everyone who might potentially be interested in the room at the same time. And so what I want to study in this lecture is sort of a similar problem to what we've studied in the last few lectures. How do we maximize either revenue or welfare in a simple mechanism design setting? We're going to restrict our attention in this lecture to single item auctions. But how do we do it when we can't run an auction because we don't know who's going to show up, and instead we're going to have to use posted prices and run the risk of potentially selling it to someone today because they showed up with a willingness to pay for the price that I posted, without the knowledge that maybe someone with a much higher valuation would show up tomorrow. Okay, so let's write down a simple model to sort of ground the problem we're talking about, but maybe think about selling something like a used car, right? So you personally might sell a one car. There's definitely like a supply constraint here. You only have one car, so it's sort of we're not exactly finding like a market equilibrium price here. And people are gonna knock on your door, and you're gonna give them a once over, and you'll decide on some price to offer them. Okay, so we're gonna allow for the fact that there might be more than one recognizable type of buyer, right? It's fine if K here is 1, but we're going to allow that there might be more than one type of buyer And you can potentially offer different prices to different types of buyers, right? So if someone shows up at your front door, you know, like in a suit and a monocle and a top hat, then maybe you're going to offer them a higher price than you'd offer someone else. And so in our model, you know, when a buyer shows up, I can tell what type he is. And my knowledge of his type is encoded in some distribution over what I imagine his valuations are. And buyers from each type will have their valuations drawn from potentially different known distributions. So a buyer of type I will have his valuation drawn independently from some distribution DI. Okay, so again, if they show up in a top hat and a monocle, maybe I imagine that their willingness to pay for whatever I'm selling is on average higher than if they, you know, show up in jeans and a t-shirt. And the key thing here is that the buyers are not all going to show up at once. If everyone showed up at once, I could just run a second price auction and sell it to the person with the highest valuation. I could have a reserve price. I could use all of the tricks we've learned so far to maximize either welfare or revenue. But the issue here is that the buyers are going to show up one at a time and then they're going to leave. And what I can do is, you know, after looking each buyer up and down and like observing their type, I can offer them a price, PI. Okay, potentially different prices for different types of buyers. And what's going to happen is that if the value for the buyer that showed up today was bigger than the price that I offered, then he will buy the item, okay, at the price that I offered. I will make some revenue PI. But if the price that I offered him was too high, if he didn't want to pay, then he's going to leave. Okay, so there's this sort of like opportunity that if I offer, you know, there's this trade-off here. On the one hand, I don't want to offer too low a price. If I offer too low a price, then the buyer will, well, they'll buy the item, but I won't get very much revenue. On the other hand, if I offer too high a price, they'll just walk away and I won't have the opportunity to, at some later point, try to offer them a lower price, right? Like I don't know the future. I don't know who's gonna come in the future. And so it might be that the person who showed up today actually was the, you know, person with the highest valuation, but I you know, mistakenly sent him away because I offered him too high a price. And that's sort of the difficulty in this problem. And so the question that I want to ask this lecture is, given knowledge of this setup, in particular, given knowledge of these distributions, DI, one for each type of buyer, are there ways for me to set the price as PI so that despite the uncertainty that I face, despite the fact that I have to make these decisions about whether to sell to a particular person or not online before I see who's going to come in the future, that I'm able to approximate either the welfare or the revenue that I could have obtained with the optimal auction, you know, with either the VCG mechanism or the revenue optimal auction, if only I had had everybody here up front. Okay, so does this setup make sense? You know, before we dive into the technical details of how we're gonna solve it, does the problem that we wanna solve make sense? And is it clear why sort of the auction machinery we've built up is not sufficient to do it? Question, are we assuming that there's one buyer of each type, or do we know how many buyers of each type there are? Yeah, so the assumption is going to be not just that there's one buyer of each type, although there could be, but I guess we are gonna know, well, we'll see on the next slide. There can be many buyers from each type, although there don't have to be. You know, if you know a lot about the world, maybe every buyer has their own type. On the other hand, if you have sort of a coarser understanding of the world, maybe there's, you know, just two types or just one type. But we'll see on the next slide when we sort of pin down the methodology the mathematical tools we're going to use to solve this, that we are going to assume that we sort of know ahead of time how many buyers there are of each type. So we are going to have to know how many draws we're going to see from each distribution. Another question, do we have k different stores, one for each buyer, that aren't aware of the other prices? No, so there's only one thing that we're selling. There's only, so think about, like, we have one item, like a car, and we have to give it away to, or sell it to someone. And so we are one seller, and we are going to keep offering these prices until either the car is sold to somebody or until there's no more buyers. Do we know the order that the buyers are going to come in? We don't have to know the order, no. So I think, what we do need to know to make the solution that we're going to derive work is the number of buyers from each type that are going to show up, but we don't need to know the order. Good questions. Any other questions? All right. So let me describe for you a slightly different mathematical game that we might consider, and then we'll see how this maps pretty cleanly onto the problems that we want to solve, and we'll sort of solve this this mathematical game, which will solve our auction problem. So here's the idea. Suppose that you are a gambler, and what's going to happen is in each of n steps, you are going to be offered some prize. Okay, and the value of this prize, the prize at step I, which we'll call PI, is drawn from some distribution GI. Now, you know ahead of time what all these distributions are. Okay, so you're going to know ahead of time exactly the distribution you will face at step 1 and step 2 and step 3, all the way up through step n. But you don't know the realization. You don't know what the actual value of the prize is that you're going to be offered at step I until you actually reach step I. And at step I, after you see the value of the prize, pi I, that you're being offered at that step, you face a decision. You can either put this prize in your pocket and accept it, okay, and that'll stop the game. You won't get to proceed for any future steps. Okay, and in that case, you will get profit pi I. Or if you think you can do better, then you can take your chances and you can reject this prize and proceed on to the next round. Okay? So the issue here, of course, is that although you know the distribution on prizes in future rounds, you don't know their actual realizations. So you have to make these decisions about whether you want to accept the prize and end the game or keep playing the game in the absence of some important information, right? Like on the one hand, you don't want to accept a prize that's too small because maybe you would have had the opportunity to get a much bigger prize if only you'd continued the game. On the other hand, you don't want to be too aggressive about rejecting prizes because it might be that you reject what turned out in hindsight to be the highest prize. Okay? And, so we might think about how you should play such a game. How should you decide a strategy given the knowledge available to you that will tell you when you should actually keep a prize and end the game? And one very strong benchmark that we might compare ourselves to is the benchmark of a prophet. So a prophet who could foretell the future and could therefore always sort of oracularly select the prize that has highest reward. Okay, so like this prophet benchmark who knows the future, this is an extremely strong benchmark because no actual algorithm or policy could ever actually achieve this because there's sort of inherently some informational uncertainty. It might be that because you're seeing an unusual draw, that the prize that ended up being the highest value was not the one you would have expected given the distributions that the prizes were drawn from. Nevertheless, if we could compete with this profit using some actual realizable strategy for playing this game, that would be a very strong guarantee. Okay, so the profit that our profit could make would be the expected value of the maximum realized reward, right? Because on every single instance, the profit would have knowledge of the maximum realized reward that would show up in this stream of offers. And every single time he would reject offers until he got to the maximum reward offer, and he would accept that. And so since every single time he gets the highest reward, his expected profit will just be the expectation of the highest reward, and the expectations over the draw of all of the rewards. Right? Does that make sense? That this is some game in which the player has sort of some inherent informational disadvantage. He has to, he's trying to pick the highest reward, but he has to make the decision before he knows what the future rewards are going to be. The best he could possibly do is pick the sort of highest reward every single time. That's not possible, but that's at least a benchmark that we could compare ourselves to. And so the natural question here is, how well can we actually do, right? We, in this game, are at an informational disadvantage. We do not have the ability to predict the future. We can make decisions as a function of the information we have available, which is just the sequence of realized rewards from day one through today, plus knowledge of the distributions on future days, but not the rewards that will be drawn from those distributions. Okay. And sort of a remarkable tool that's going to be useful for us is what's known as the profit inequality. And it's going to tell us that not only is there a strategy for playing this game that does pretty well compared even to this oracular profit, this sort of impossible strategy we could never implement, it's going to tell us that there's actually a very simple strategy that will allow us to compete with this profit. And it's going to be a threshold strategy. So a threshold strategy is possibly the simplest strategy you could imagine in this game. And a threshold strategy simply fixes some threshold t, and the rule it uses to decide whether it should accept a particular prize is it just compares the prize to this threshold. Okay, the same threshold every time, and it accepts the prize if and only if its value, pi I, is larger than the threshold. Okay, so what a threshold strategy ends up doing is just selecting the first prize that happens to cross this threshold. And already you might notice an immediate connection between the sort of gambler setup that we've been talking about over the last 2 slides and our original pricing problem, at least when it comes to welfare. Maybe it's not obvious yet how to think about this, how this is going to be useful for revenue. But at least when it comes to welfare, there's sort of an immediate connection between threshold strategies in our gambler's game and how they connect to the ultimate profit of the strategy, and posted pricings, fixed pricings in our pricing game, and how they connect to welfare. Right, in particular, the thresholds correspond to prices, and the rewards correspond to bidder valuations. And just to observe this connection a little more explicitly, if I post a price P, well, who do I end up selling it to? I end up selling to the first bidder who shows up, whose valuation is bigger than P, right? Because everyone before that turns down the offer, and the first bidder whose valuation is bigger than P accepts the offer. And if I'm interested in welfare, then what is my sort of reward for accepting a bidder with valuation VI? Well, it's exactly VI, right? Because if I'm interested in welfare, I just want to give the item to the person who wants it the most, and the welfare of the outcome of a single item auction is just the valuation of the person I gave the item to. Okay, so the price corresponds to the threshold, and the payoff corresponds to the welfare. The payoff here does not correspond to the revenue because I don't get, VI units of revenue. I only get P units of revenue. That would be like if my payoff in this gambler's game was T rather than pi I. Okay, so there's not yet a direct connection between this gambler's game and trying to maximize revenue, but there's a pretty direct connection between strategies, threshold strategies in this gambler's game and the welfare I can obtain with a single posted price. Does that make sense? Okay. And with that connection in mind, here's the profit inequality that's going to sort of drive our results from today, and which we're going to prove on the next few slides. Okay, and this is kind of remarkable. What it says is that for every instance of the gambler's problem, for every single set of distributions G1 through Gn, no matter what they are, there always exists a threshold strategy, like a fixed number T, such that if we look at the expected reward of this threshold strategy, it is at least half of the expected reward that a profit could obtain. Right, so we're getting within a factor of 2 of the profit's reward, the profit's profit. And remember, the profit strategy is not realizable because the profit has information that we don't have. So even the optimal strategy, right, even the optimal actual implementable strategy would not be able to obtain the profit's reward. And what this is saying is that there is a strategy that has the simplest form you could ever imagine, right? It's just sort of comparing all of the rewards to a single fixed threshold that does within a factor of 2 of this oracular unachievable benchmark. Does that make sense? Okay, so let's prove the profit inequality. So let's fix some notation and some language, and then the proof will actually be pretty straightforward. So first, a couple simple pieces of notation just to simplify the notation that we need going forwards. So if I have a real number z, I will just write z plus to denote the positive part of that number, which is to say it's just the maximum of z and 0. If z is already a positive number, then z plus is just z. If z is a negative number, then z plus is just 0. Okay, it's the positive part of the number. And instead of always having to write max I of pi I for the maximum realized reward, I'll just write v star. Right, so v star is the maximum realized reward over an entire sequence of rewards. V star is the profit, the reward that the oracular benchmark, the profit, would always be able to achieve. Right, we want to show that we get reward that is within a factor of 2 of the expected value of v star. And in fact, like, not only is the strategy that's going to compete with the profit simple in that it's a threshold strategy, the threshold is also extremely simple. So the threshold that we're going to use is just always half of the expected value of v star. Okay, so all these distributions, right? The premise is all of these distributions, d1 through dn, and so you can compute what is the expected value of v star. right? You can do that just by sampling if you wanted. And the threshold that we're going to use is just half of that. Okay, so our threshold rule is always going to be to sell to the first bidder, say, whose valuation is at least half of the expected value of V star, which would just correspond to setting a posted price that applies to everybody equal to 1/2 V star. 1/2 the expectation of V star, because of course V star is a random variable. We don't know what its realization is when we start the mechanism. And we already discussed this sort of direct connection between threshold strategies in this gambler's game and fixed pricings in our welfare maximization problem. And just to sort of avoid confusion, I will use the language of the economic application while proving this theorem, the profit inequality, which of course holds in this sort of more abstract, gambler's game. And so just to make that connection clear, if I say the item is unsold at the end of the interaction, that is equivalent to saying that we as the gambler failed to accept any of the prizes. And if I say that the item was sold, that just means that we as the gambler accepted one of the prizes. Remember, there was this connection between accepting a prize, pi I, because it crossed our threshold t, and selling to bidder I because their valuation vi exceeded our price p. And with this, with the language of the economic application in mind, the way we will prove the profit inequality is we will decompose the expected social welfare that we obtain, or equivalently the expected reward that the gambler gets, as the sum of two things. On the one hand, the expected revenue of the mechanism, and on the other hand, the expected utility of the buyer. Okay, and we'll lower bound both of these things. Okay. So what's the thing that we want to show? We want to show that if we use just a fixed price, in fact, the same price for every type of buyer, that we will arrive at an allocation that has high expected welfare. Or equivalently, that if we are a gambler playing this game, that if we use a fixed threshold strategy, then we will get a large reward. So let's think about this. So suppose we end up selling to some buyer I at price P. Okay? Remember, there's this connection between the two settings. Selling to a buyer I just corresponds to selecting reward I. Okay, so suppose we sell to buyer I at some price P. Well, in that case, we as the seller would get revenue P, right? Like when I sell to someone at price P, they give me P dollars. And on the other hand, the buyer would get utility VI minus P, right? The buyer would get the item, so they'd get utility VI, but they'd have to pay me P dollars, so their overall utility would be VI minus P. And what I want to observe is that the welfare that would be obtained in this solution, which of course is just VI, is the sum of the revenue plus the buyer's utility, right? The welfare, and the welfare for a single item allocation, where I just give the item to buyer I, that's just VI. That is the sum of the buyer's utility, which is VI minus P, plus the revenue, which is P. The prices cancel out, and the welfare that I'm left with is just VI. Okay? Does that make sense? This is sort of like a simple observation, but important to the proof. So if there's any questions, this is a good time to ask. Right, the observation here is just, for any realization, I can always decompose welfare as the sum between the sum of revenue and buyer utility. Right? And so if what we want to do is prove that our expected welfare is large, it will be sufficient to prove two lower bounds. To first prove that our expected revenue is large, and then prove that our expected buyer utility is large, right? Because the expected welfare is just going to be the sum of the expected revenue plus the expected buyer utility, right? Since expectations are linear, we can consider these two quantities separately, and that's going to be our strategy, to separately prove lower bounds on expected revenue and expected buyer utility, so that when we sum them together, right, maybe we can't say that either of these two things will be large in isolation, but we want to prove bounds that when summed together will give us a good bound. And so let's consider each of these two things. What is the expected revenue that I get if my plan is to offer everybody who shows up just a fixed price of P until the good is sold? Well, there's two possibilities, right? On the one hand, maybe I will sell the good to somebody, in which case my revenue is P, right? If I sell the good to anybody, then I get P dollars. On the other hand, maybe nobody was willing to pay P dollars, and so in that case, I don't sell the good to anybody, in which case my revenue is $0, right? So my expected revenue is just P, the price that I set, times the probability that the item was sold, that I sold the item to one of the N bidders who showed up, okay? And remember, we're trying to prove this theorem for a particular value of P. The price that we proposed using, the threshold that we proposed using in this exercise was exactly half of the expected value of the maximum realized valuation. Okay, and so we can plug that in and just conclude that our expected revenue is 1/2 times the expectation of V star, the expectation of the maximum realized value, times the probability that the item is sold. Okay, so this is some expression. We can't yet say whether our expected revenue is going to be high or low, because it's very hard to say whether the probability that the item is sold is going to be high or low. But at least this is a correct expression, in fact, an exact expression for our expected revenue. Okay, so we have some expression for expected revenue. How about buyer utility? Remember, if we can get an expression for expected buyer utility, then we can get an expression for expected welfare by just summing that together with our expected revenue. And so expected buyer utility is going to be a little bit more complicated, but not too much more complicated. We can reason through it. And let's consider buyer I's utility, bidder I's utility. Okay, so there's again sort of a couple of cases to consider. It might be that we sell the item before we even have an opportunity to offer it to buyer I, right? Like maybe I sell the car to the first person who shows up at my door, and so person 3 never had a chance. Their utility in that realization is definitely going to be 0. On the other hand, if I haven't sold the item before buyer I shows up, then who knows if they're going to want to buy the item, but at least they'll have the opportunity to buy the item. So if in this process we get to bidder I before selling the item, then she has the opportunity to buy. And what's her utility? Well, it's exactly going to be the positive part of VI minus P, right? Because there's two cases. Either her valuation is higher than the price, in which case she will buy the item, and her utility will be exactly VI minus P. Or her valuation is less than the price, in which case she won't buy the item and her utility is going to be 0. Right? So in either case, her expected utility is exactly equal to the positive part of VI minus P in the event that she even gets the opportunity to consider buying the item. Okay, so with that observation in mind, we can now, again, exactly write down an expression for the expected utility that buyers get in this exercise, right? We have to sum over all of the buyers of the expected utility of each buyer I. And what's the expected utility of buyer I? Well, remember, it's 0 if we already sold the item before we got to buyer I. And if we haven't, if the item was unsold before we got to buyer I, then their expected utility is just the expected value of the positive part of VI minus P. And because the buyer valuations are independent of one another, right? They're not correlated. Each buyer valuation is drawn independently from their own distribution. Whether or not I've sold the item before I got to buyer I is independent of buyer I's valuation. And so I can write this expected utility for each buyer as just the product of these two terms. I can write this as a product because the event that the item is unsold before I is independent of the value of buyer I. And so the expected utility of buyer I is just the probability that buyer I even gets the opportunity to consider buying the item times the expected value of the positive portion of VI minus P. Okay, and then we sum over all of the buyers. So again, we have an exact expression for expected buyer utility. And there's a question, just to confirm, that independence is only because the threshold itself is fixed, right? Maybe I don't quite understand the question, but oh, more question. i.e., if the seller were to use an updating strategy, it would go away. No, even if the seller were to update their price as a function of what they had observed. Well, okay, a couple of points here. So first, what is the seller even observing? Like, what information would you use to update the price? Like, the only thing the seller observes is whether each buyer decides to buy the item or not. And if we got to buyer I, like the fact that we got to buyer I means that there's only one thing he could have observed, which is that buyers 1 through I minus 1 declined to buy the item. So in fact, there's no room to have an adaptive price here at all, in the sense that you could have different prices for different buyers as a function of their distribution, but there's no room to try to change the price as a function of realizations, because there's only one possible observation you could have made up until this point, which is that nobody bought the item. Okay, so that's maybe like the first answer to your question. But the second answer to your question is still no, right? You could imagine a more complicated scenario where, like, I actually get to observe, like, after the buyer declines to buy the item, he, whispers his true valuation into my ear just to make me feel bad, right? And so now I could potentially update prices as a function of what happened in the past. Well, still, the price, whatever it would be some arbitrary function of the valuations of bidder 1 through I minus 1. And since those valuations are independent of bidder I's valuation, the price would also be independent of bidder I's valuation. So this would be true even if we had an adaptive strategy on the one hand, and on the other hand, the setting that we're in right now makes it impossible to have an adaptive strategy. Does that make sense? Great. Good question. Okay, we will talk about adaptive strategies in the coming lectures. So that these are good points to have in mind. Okay, so just to recap, we have an exact expression for expected buyer utility, and it's pretty simple. It's just the sum over all of the bidders of the expected buyer utility of bidder I, and buyer I gets expected utility equal to the expected positive part of VI minus the price exactly when the item wasn't yet sold before we got to bidder I. And because that event is independent of the buyer's valuation, we can just multiply the expectation of the positive part of vi minus p times the probability that the item was unsold before we got to buyer I. Okay, now again, let's think about these probabilities, like the probability that the item was unsold before we got to buyer 1, the probability that the item was unsold before we got to buyer 2, the probability that the item was unsold before we got to buyer 3. These are monotonically decreasing numbers, right? Like for sure, buyer 1 gets the chance to buy the item. And then buyer 2 probably still has a pretty good chance of having the opportunity to consider the item, because the only way that buyer 2 wouldn't get that opportunity is if buyer 1 had bought the item. But buyer 3 has an even lower chance of getting to buy the item, of getting to have an opportunity to buy the item, because there's 2 ways that buyer 3 could have failed to get this opportunity, right? Either buyer 1 or buyer 2 could have bought the item ahead of them. And similarly, if I look at the probability that buyer I gets the opportunity to buy the item, that's always going to be like just a smaller number than the probability that buyer I minus 1 had the opportunity. The later you are in line, the smaller the chance that the item is still around by the time you get to the front of the line. Okay, and so we have this sum in which, you know, for every term in the sum, we are multiplying some function of buyer I's valuation with the probability that the item is unsold before it got to buyer I. So if we want to lower bound this expression, we can replace all of these probabilities with smaller numbers. And here's a number that's smaller than all of them. The probability that the item is unsold after we've completed the entire interaction and have offered it to all n buyers, right? Like for sure, if the item was unsold after the whole interaction, it was unsold before I for each of the possible values of I. Okay, so all I'm going to do is I'm going to replace in each term in the sum the probability that the item was unsold before I with the probability that the item was unsold, period. That's only a smaller number, and so this lower bounds the whole thing. Okay, so I'm going to massage this a little bit more. Okay, so we've got the probability that the item is unsold. Now let's deal with this sum. So what's the sum? Well, it's the sum over the expected positive part of vi minus p. That's the same thing as the sum of the expectation is the same thing as the expectation of the sum. Okay, so I can think of this as the expectation of the sum over all I of the positive part of vi minus p. Well, the sum over all I, right, if I'm summing over a bunch of non-negative things, that sum is always going to be bigger than the maximum thing in the sum, right? Everything's non-negative, so the sum has to be bigger than every single term in the sum. In particular, the sum is bigger than the maximum term in the sum. So I can lower bound this term, which is the expectation of the sum of a bunch of things, with the expectation of the max of that same list of things. Okay, so this is at least the expected value of the maximum over all bidders I of the positive part of vi minus p, again, times the probability that the item is unsold. And I can remove this, little plus sign, right? The expected value of the maximum of some random variable, the expected value of the positive part of some random variable is only bigger than the expected part of the random variable, right? Like if I take the expectation of some random variable, there'll be some realizations that are positive, that'll push my expectation up. There'll be some realizations that are negative, that'll push my expectation down. And if I take the expectation of just the positive part, then I won't have any of those, bad realizations that push my expectation down, but I'll still have all of the good ones that push my expectation up. Okay, so this term only gets bigger, or rather only gets smaller if I take the random variable itself, the maximum overall buyers of VI minus P instead of the positive part. Okay, and once I do that, I can distribute the expectation because the price P is the same for all of the buyers. Okay, and so this is only larger than the difference between the expected maximum value over all of the buyers minus the price times the probability that the item is unsold. And finally, we can again plug in the value that we chose for our price, that we chose for our threshold strategy, right? And observe that, well, what is the expected value of the maximum overall I of VI? Well, that's just the expected value of V star, right? That was the definition of V star. V star is equal to the maximum realized valuation. On the other hand, the price that we picked is half the expectation of V star. And so we have the expectation of V star minus half the expectation of V star. And what we're left with is half the expectation of V star times the probability that the item was unsold, period, by the time we got to the end of the interaction. Okay? So we now have two bounds. On the one hand, we know that our expected revenue is half of the expectation of V star times the probability that the item is sold. It's exactly equal to that. And we also know that our expected utility, and we don't have an exact expression for our expected utility, but we know that it's at least as large as half of the expected value of V star times the probability that the item is not sold. Okay? So in isolation, we cannot say that either of these two things is large, right? Like we cannot say that the expected revenue is large because it might be that the item is not sold with very high probability. On the other hand, we can't say in isolation that buyer utility is large in expectation because it might be that the item is sold with high probability. But what we can say is they cannot both be small simultaneously. Okay, so just to sort of finish things up, we noted realization by realization that welfare is always revenue plus utility. And so expected welfare is always expected revenue plus expected utility. And we have bounds for each of these things. So expected welfare is just half of the expected value of V star, our benchmark, times the probability that the item is sold. And expected utility is always at least half our benchmark, the expectation of V star, times the probability that the item is unsold. And we can combine like terms. And so we know that our expected welfare has to be at least half our benchmark times the sum of two probabilities. The probability that the item is sold plus the probability that the item is unsold. And we have no idea, since we don't know what these distributions are, whether the probability that the item is sold is going to be high or small. We don't know whether the probability that the item is unsold is going to be large or small either. But we do know that whatever happens, the item will either be sold or it will be unsold. And so we know that the sum of these two probabilities has to be exactly 1, because one of these two outcomes has to happen. And so that's the full proof. The expected welfare has to be at least half of the benchmark welfare. Okay, does that make sense? The proof is quite simple, but a little bit slick. So I just want to make sure people understand it. What's our expected welfare if we just select the person with the highest expectation distribution and then sell to them for price 0 and give everyone else price infinity? Let's sort of parse that, right? So first of all, what do we mean the person with the highest expectation distribution? Suppose, for example, that everyone had their valuation drawn from the same distribution. Okay, suppose everyone's valuation was drawn uniformly at random between 0 and 1. So they all have the same expected price. If we just sell to the first person at price equal to their expectation, which is like 1/2, we will, at best, let's follow your suggestion exactly. So we'll set for them price 1/2, and we'll set for everyone else price infinity. And so we'll either sell to the first person or we won't. Now, 1/2 does happen to be the revenue maximizing price if we're selling to one item to one buyer, right? And so as we saw last class, we will make expected revenue 1/4, because half the time they'll be willing to buy the item, and when that happens, they'll give us $0.50. On the other hand, this is much worse than the optimal revenue, which will be close to 1, right? Because if I look at the maximum realization of n uniformly random variables, it'll be essentially 1. It'll be 1 minus 1 over n. Okay, and so it'll approach 1 as n goes to infinity. And so just picking the first buyer and selling to them at their expected valuation gets revenue that is, gets welfare in this case, that is substantially worse than if we set a higher threshold. Does that make sense? But like the issue is, if everyone has the same distribution in this case, if we decide to just pretend that it's a single item auction or to a single bidder and just sort of kick everyone else out, then we are losing the benefit of having many draws from this distribution, which will increase the benchmark value but won't increase our own realized value. Make sense? Yeah. Good question. Okay. So just to sort of like note the immediate implications of the profit inequality. What it means is that we don't even have to use the full power of this pricing setup we used, right? Like there might be different types of buyers drawn from different distributions, but actually this threshold strategy is going to use the same price for everybody. Right, we're just going to offer, we're just going to like put a sign on the car. We're going to say, the first person to knock on my door and offer me price P gets the car. And what this is saying is if we choose the price P correctly, okay, if we choose the price P to be half of the expected value of the max realization, then even though I don't know, say, what order people are going to show up in, and of course I don't know the realization of their values, I will still in expectation get I will achieve half of the expected welfare of the VCG mechanism, even though to run the VCG mechanism, I would have had to aggregate all of the bidders ahead of time, which would have resolved for me this uncertainty about what buyers' valuations are. This is saying even without needing to sort of go to the logistical hassle of aggregating everyone together so that I don't have any uncertainty about the realizations of people's values in the market, with this simple, posted price, no coordination required at all, I can do, at least half as well. Okay. And so let's see if we can extend this to revenue. So if you remember, we've already talked a little bit about revenue, right? Like if we look at the if we look at our derivation of the profit inequality, the first thing we did is we, as a function of the price P, said something about revenue. But unfortunately, we weren't able to say very much about revenue, right? Like at no point in this argument were we able to say that revenue was large, right? And at no point in this argument were we able to say that expected utility was large. The only thing we were able to say is at least one of these two terms has to be large, and that's what let us conclude that welfare had to be large. But from what we've done so far, we really don't have much to say about revenue. But fortunately, we're going to be able to use some of the tricks from last lecture to give the same result about revenue, that we can obtain at least half of the revenue of the optimal auction. And maybe that's not so surprising if you sort of reflect on what we did last lecture. right? Because what we did last lecture in deriving this revenue optimal auction was essentially to reduce the problem of revenue maximization to the problem of welfare maximization, and then apply our known techniques for maximizing welfare. Okay, well, we now have an algorithm for achieving a good welfare bound in this new setting. So maybe we can use exactly the same reduction. So just to sort of recap what we proved at last lecture, what we showed is that for any monotone allocation rule that is dominant strategy truthful, we can always make it dominant strategy truthful by pairing it with the appropriate pricing rule, which we derived 3 lectures ago. We can express expected revenue as something that looks kind of like expected welfare. Okay, it's expected virtual welfare where we've replaced what would be just bidders' valuations in the welfare objective, which, right, that would just be the sum over all of the bidders of their valuation VI times their allocation X. We were able to replace these valuations with what we called their virtual valuations, right? There was this function we derived last time as a function of Bayer I's distribution that just transformed Bayer I's valuation monotonically into what we called their virtual valuation. Okay, it involved subtracting off some term that depended on their distribution. And what we showed is that if you have an algorithm for maximizing virtual welfare, then you maximize revenue and expectation because your expected revenue is exactly equal to your expected virtual welfare. In particular, the mechanism that achieves the best expected revenue, which again we derived last time, and the benchmark that we want to compete with here, right? This is sort of the equivalent offline benchmark, the revenue that we could get if we were able to aggregate everyone together in the same room and actually run an auction. This benchmark is just equal to the expected value of the maximum of the positive part of the virtual valuation. Because remember what the optimal allocation rule is for the revenue optimal auction. It just gathers everyone together and it gives the item to the person with the highest virtual valuation if the highest virtual valuation is positive. And if the highest virtual valuation is not positive, it doesn't give the item to anybody. And so realization by realization for the optimal auction, the term inside the expectation is equal to the highest virtual valuation if it's positive, because that's who we give the item to, and otherwise equal to 0, which is just another way of saying that realization by realization, the virtual welfare obtained by the revenue optimal auction is just the maximum over all buyers of the positive part of their virtual valuation, because we give it to nobody if the virtual valuation is negative, and so our virtual welfare in that case is 0. That's why we take the positive part. Okay, does that make sense? So the optimal revenue, the optimal value of our expected revenue is exactly equal to the expectation of the maximum overall buyers of the positive part of their virtual valuation. Does that make sense? That's sort of almost direct from what we derived last lecture. Okay, so let's try to cast this into our setting so that the procedure that we just came up with for approximating the optimal welfare can be used to approximate the optimal revenue. Okay, so when we were maximizing welfare, we defined the rewards pi I in this gambling game just to be VI. Okay, what we're going to do now is we're going to define the rewards in our gambling game pi I to be the positive part of the virtual welfare of bidder I. Okay, we can do that. There's some distribution over VI, therefore there's some distribution over phi of VI. Therefore, there's some distribution over the positive part of phi of vi. Remember, there was no constraint at all about what our distributions were in this gambler's game. We didn't use anything about those distributions to prove the profit inequality. And so when we do this, the benchmark in the gambler's game, the expected value of v star, well, it's just the expected maximum value of all of the rewards, which is just opt. Okay, so if we define the rewards this way, then the expected benchmark, or the benchmark in our gambler's game that we already know how to compete with is equal to the expected revenue of the revenue maximizing auction. And so we can, again, in this setting, apply the profit inequality. Okay, and in the setting of the gambler's game, we know that if we use a threshold strategy in which the threshold is at least opt over 2, then we will obtain virtual value that is at least 1/2 opt. Right? This is a direct application of the profit inequality, which just tells us that in any possible realization of the gambler's game that we've been talking about, a threshold of the oracular profit benchmark divided by 2 will achieve within a factor of 2 of our benchmark. And we've rigged things up here so that the benchmark that we're competing with in the gambler's game is exactly the optimal expected revenue of any truthful auction. And so the only question is it possible to implement this threshold strategy in an actual pricing situation, right? Because the thresholds are now on the virtual values, not on the values. But the answer is yes, right? Because if I want to accept any reward that crosses threshold t, okay, and the rewards are phi of vi, the positive part of phi of vi, then I can turn that into some corresponding threshold on the values by just applying the inverse phi function. Okay, so setting a threshold of opt over 2 on the virtual value is the same thing as setting a threshold of the inverse phi function applied to opt over 2 on the value, right? Because the phi function maps values to virtual values, the inverse phi function does the reverse. Okay, which corresponds, again, to setting for bidders of type I a posted price of pi equal to this inverse virtual valuation function of opt over 2. Okay, so opt over 2 is going to be the same for everybody, right? The threshold is the same for everybody. It doesn't depend on the reward distributions, but now the virtual value functions might be different for people of different types, right? The virtual value function for buyers, for bidders of type I, depends on the distribution from which their values are drawn, depends on DI. So the threshold on the virtual values is the same for everybody, but because the virtual valuation functions are different for different buyers, now we actually have to set different prices, different thresholds on the valuation functions for different buyers. Okay, and just again to make sure we've dotted all of our I's and crossed all of our T's, we derived this equivalence between revenue and expected virtual welfare for monotone allocation rules. But note that that's fine, because what we've come up with at the end is indeed a monotone allocation rule. Our allocation rule is very simple, right? A posted price corresponds to the following allocation rule. If your valuation is above the posted price, you get the item. If your valuation is below the posted price, you don't get the item. So it's definitely monotone. And so again, fortuitously, starting from a characterization that holds for monotone allocation rules and going through some kind of unconstrained optimization, we have arrived at an allocation rule that is indeed monotone. And so our conclusions are correct. This is an auction format that, or rather a posted pricing that allows us to get within a factor of 2 of the revenue that we could get even if we had bothered to gather everyone together. Okay, so note that for welfare, we only needed to use a single posted price, right? For welfare, we just needed to, put a price tag on the car. For maximizing revenue, we do have to offer different prices to different types of bidders, right? It might really be that I need to offer different take it or leave it offers to people who show up in fancy suits, driving fancy cars, than I do to people who show up in the bus in jeans and a t-shirt. But if I do that, I can still approximate the revenue that I could have gotten had I gathered everyone together and run an auction. Okay, so that's it for today. I'm gonna stop the recording, but I'll hang around for a few minutes to take questions.